Well, here we have a wonderful Calc 1 exam too. So this is getting into more of, we know derivatives. Let's dive deeper into derivatives, their rules, maybe even do some applications. Nice. Now this was from fall 2024. Great vintage. Getting into that multiple choice. Life is good. And of course, as always, if we want credit, make sure you put your name on it. And so, with that out of the way, we're ready to begin. Okay, let's find out. We're in our multiple choice to begin. What is the absolute minimum? And notice they even highlighted that for us. They put italics, drawing our eye to the idea, hey, this is a problem related to absolute minimum. That was very nice of them. And our function is f of x equals 16x cubed plus 12x squared minus 24x on the interval from -1 to 1. And so as we look at this, we say, absolute minimum. What's that one? Well, that's one where we go, we're making a list and checking it twice. Gonna find out which points are nice. Absolute, max, and min are found. We start by putting the endpoints. Those will always be on our list. And remember, our list is our x values where we might have a max or min, and endpoints should always be included. The other place to look are from the derivative. So we take the derivative, f prime of x. Well, what would that be? 48x squared, 24x minus 24. All right, we'll factor out a 24. 24 times, that would be 2x squared plus an x minus 1. Now, I like to think we have nice teachers, and we generally do, which means we should anticipate things like this to factor. You say, all right, well, how should it factor? Because we have that 2x squared at the front, when we're thinking of factoring, we say, well, that's going to be our two pieces. The only way to break 2 up is as 2 and 1. So we say, all right, 2x and x. And this 1 on the end, only way to break it up is as 1 and 1. And the fact that it's a minus means one of these should be a plus, one of them should be a minus. Now, let's think of it. If we put the plus here, it would be plus 2x minus x, which looks positive for us, so that's good. But if we put the plus here, so that this was a minus, it would be minus 2x plus x, which doesn't match. So, in particular, we have a plus and a minus. All right, good. Now, with that out of the way, what do we say? Well, undefined? No. Polynomials, beautiful function. So what are we looking for? The zeros. The zeros are our heroes. They're going to tell us where to look. And for us, we say, well, 2x minus 1, well, that would be 0 at x equals a half. And x plus 1 would be 0 at -1. Well, okay, look, we already knew about the -1, but a half, that wasn't on our list yet. And quick check, is a half between -1 and 1? If it wasn't, we wouldn't put it on the list, but it is, so we put it on our list. And now we're done. We've made our list. Now, that's not to say our answer is on here because it doesn't match any of these. Our list is where the x values are, but when we're talking about absolute, max, and min, we're talking y values. So to get that, we need to plug it in. So we're going to plug in our values. So we're going to plug in the function at each one of these points. Now, some points are easier than others. When you plug in 1, that's just adding coefficients. So that would be 16 plus 12, subtract 24. Well, that's a 28, subtract 24, and that would give you 4. You're like, we've won. It's an option. Oh, be careful. They know it's an option. They're trying to get you to bite. Make sure you check all the points. It's not that one of these values, we have to get all the points checked. Now for -1, -1 cubed times 16, well, that would be minus 16. And then here, -1 squared is positive 1, so plus 12. And now here, minus 24 times minus 1 is a plus 24. Okay, whoops, 24. I can write 24. So 24 plus 12 makes 36. Subtract 16, and that gets you a positive 20. Not a negative 20, a positive 20. And now the one that might take a little bit. Okay, f of 1/2. Well, let's just write it down here. 16, a half cubed is 1/8. Plus 12 times a half squared, 1/4. Minus 24 times a half. Okay, great. 16 times 1/8 is 2. 12 times a quarter, 3. 24 times a half, 12. 2 plus 3 minus 12, negative 7. Now, here's our grand finale. When we're looking for the absolute max and mins, it's these numbers we look at. Those are the y values. Which one's the smallest, because we're after the min? Negative 7. So our answer is C, negative 7. All right, good. Now, before we leave, I just want to point something out. They planted some traps for people who are like, I just have to check a couple of points. Let me check the endpoints, and I'll throw in 0. And if you throw in 0, you'll get 0, 0, 0, and that looks very tempting. Or if you only check endpoints, that looks very tempting. So do the work. Be methodical. They know what people look for, and they're like, we'll have you look somewhere slightly off. And so that's why you do the work. And on a personal, I'm sorry, I know we should get there. I'll do the rest of them faster. This is my problem. My country. I wrote this one. I did. And you're probably thinking like, it feels like a Steve problem. Thank you. All right, and now for the rest of them. Okay, number 2. Suppose g of x and h of x are differentiable functions. H inverse of x exists. Okay, that's good to know. And the following statements are true. So we have information about the derivatives of g, values of h, and values of the derivative of h. If f of x equals g of h inverse of x, find f prime of 2. All right, so now we're going to try to dig in and say what's going on here. So we want f prime of 2. So let's find f prime of x. So we say, well, what is f prime of x? That's the derivative of g of h inverse of x. We say, all right, let's start digging into that. We have a function in a function. Chain rule. So this would be g prime, leave the inside alone, times the derivative of the inside. Okay, great. And now, chain rule. Now we have the derivative of inverse rule. Well, how does that work? Well, there's a nice way to do it. It's 1 over h prime of h inverse of x. Okay, so that's the derivative of the inverse rule. And the good news is it's just x on the inside, so we've now gone all the way down. Well, what do? We're going to plug in 2. All right, so wherever we see an x, we're going to put a 2. So let's start by finding h inverse of 2. So what we do is we come to the h's, and we want h inverse of 2. So that's not saying, look at h of 2. It says, when does h have an output of 2? Well, that's right here. H of 1 equals 2. So that tells us, h inverse of 2 equals 1. So at this time we say, okay, so f prime of 2 is g prime of 1, right, because we're h inverse of 2, times 1 over h prime of 1, right, because 1 over h prime. Okay, good. Now we just have to say, what do we know about g prime of 1 and h prime of 1? Well, that's the information in here. G prime of 1 is negative 6, and h prime of 1 is 2. So this is equal to negative 6 times 1 over 2. And if you take negative 6 times a half, you get negative 3. So the answer was D. All right, good, good. Know your rules for taking derivatives and derivatives of inverses and chain rule. Chain rule, that's most important rule. Most important rule. All right, number 3. Suppose f of x is x to the power x squared. What is f prime of x? Now, notice what's going on here. This is a function where we have a piece of it down, sort of what I would call downstairs, not a denominator downstairs, but down here, and a part of it upstairs. And like, oh, well, that's not good, because we have nice rules if it's like x to a number. We have a nice rule if it's a number to x, but now it's like something with x to something with x. So we'd like to somehow have a rule. We do. So this is going to use logarithmic differentiation. Now, there's lots of ways to do this, and I am slightly biased, so I'm going to do it the way I would talk about it. And which is to say, if I want to take a derivative of any function at all, what I can do is I can say, take that function times it by the derivative of the log of the function. Okay? This is logarithmic differentiation. Now, it may not be the process that you've learned, but it is the way that it works. Now, why logs? Well, logs have wonderful abilities, one of which is it can bring exponents down. So that's why this is going to go back to logarithmic differentiation, because logarithms simplify the expression. So for us, we say, the derivative of x to the x squared is equal to x to the x squared. And so suspiciously, we say, we should have an x to the x squared there. We're probably thinking it's going to be a or b, because none of those have an x to the x squared. But let's keep going. The derivative of log of x to the x squared. And remember what we said. Because of properties of logarithms, this x squared can come down. Nice. And why is that nice? Well, now we have something which is a smaller problem. And in particular, it's the kind of problem that we know how to deal with. Product rule. So when we add a function to a function, we don't have a rule. But a function times a function, rule, product rule. All right, so we have x to the power x squared. Product rule says what? Derivative of the first, 2x, times the second, plus the first, times the derivative of the second. Okay, so this is a way to write the answer. So we start saying, well, does anything have all these pieces? We already mentioned the x to the x squared, good. And I say 2x log x, well, that's a 2x log x. And x squared times 1 over x is x. So good, so this is the right answer. Now keep in mind, functions can be written in different ways. So you have to think about, like, is this the way that they would have written it, or which one of these is it equivalent to? There's usually not going to be very creative, but just keep in mind, if it doesn't look exactly like it, doesn't mean that you got it wrong. It means like, well, maybe there's a small tweak, like, they changed the order, and they multiplied x squared times 1 over x. But anyways, the answer was B. All right. Number 4. The derivative of arctangent. Are you sure you didn't write this one, Steve? I'm positive. I mean, I like arctangent, but I wouldn't have written this one. Derivative of arctangent of x squared. Okay, so what's being tested here? 2 things. 1, chain rule. Function x squared inside the arctangent. And second thing, do you know the derivative of arctangent? Well, I hope we know both. So let's recall the derivative of arctangent. So let's say the derivative with respect to u of arctangent of u, well, that would be 1 over 1 plus u squared. Okay, so already we're suspicious it should be either b or e, because that's the only thing that has a 1 over 1 plus. Okay, so what's going to happen? Well, when we take the derivative of arctangent of x squared, we say, hey, chain rule, take the derivative of the outside. Derivative of the outside is 1 over 1 plus inside squared. So 1 over 1 plus inside squared. Chain rule then says times that by the derivative of the inside. The derivative of x squared is 2x. And so, well, that's 2x over 1 plus x to the fourth. Aha! B. Now, there's various things that they wrote down here that can throw you off. They said, just say arctangent of the derivative. Well, okay, that's not how the chain rule works. Or here, they said, first take the derivative of the inside and then plug it into the derivative of the arctangent. No. That's not how chain rule works. Make sure you know your chain rule. And then this secant squared, what? Where did that come from? Well, that's the derivative of tangent. So it's like, it's trying to throw you off your game, right? No, they're not going to throw us off our game. We're going to win this game. We're going to do great. All right, number 5. Which of the following values would you obtain by using the linearization of f of x equals the cubed root of x at 125 to estimate the cubed root of 128? Now, you may not be immediately obvious, but you kind of look at these numbers and you say, hey, they're all kind of close to 5, right? Well, yes. And so that's a good clue. The cubed root of 125, that's the cubed root of 5 cubed, which is 5. Now, let's just, before we do anything, let's point something out. How does 128 relate to 125? It's bigger. So what should be true about the cubed root of 128 versus the cubed root of 125? It should be bigger. So what does that tell us? It tells us we should not expect A or B, because those are smaller than 5. We're looking for something bigger than 5. And honestly, before we do this, I'm kind of leaning to C. Maybe D, but E seems way too big. Sometimes you can get a lot of intuition about what answers are right or not. And if you can eliminate some, that can be very helpful. In fact, sometimes the easiest way to answer a question is to say, let me eliminate possibilities. Because if I can say, these 4 things are not possible, it's got to be the 5th item. All right, now they used a fancy word here, linearization. And we're like, whoa, what does that mean? What's a linearization? Well, that's just another way of saying tangent line. That's it. And like, oh, really? Yep, that's it, tangent line. So we say, okay, we have our function. F of x is the cubed root of x. And so we'll write some things down. F of x, cubed root of x, we'll turn that into a calculus-friendly notation. I call it calculus-friendly because it's going to follow the rules. So our rules look like x to a number. So instead of using this notation, which stands for cubed root of x, we'll use x to a number to stand for cubed root of x. And then it's like, nice. It's set up just to follow our rules. Beautiful. What is the derivative? See, now that's why it's a friendly way. 1/3 x to the minus 2/3, which, by the way, is the same as 1 over 3 times x to the 2/3. Now, we need to know what the values are at the point we're interested in. So at 125. So we say, cool, we're going to plug in 125. Well, we've already done the work. This is 125 to the 1/3, and that is, as we mentioned here, 5. Now, this is actually the important part, because this is going to tell us how much we change. So f prime of 125, that's 1 over 3 times 125 to the 2/3. Now you might think of like, oh my gosh, I got to square 125. No, you don't. It's not that it's important that you know what that value is, because it's a number. It's like a big number. It's like 15,625, something like that. I don't know. It's big. But remember, we're doing 2 things. 2/3. So you have a square and you have a cube root. So don't try to make things big then small. Go small then big. You take the cube root of 125. what would that turn out to be? Well, that would turn out to be 5, because we did it up here. And then what's 5 squared? Well, it's 25. So 1 over 3 times 25. Let's not simplify it quite yet, because we may need to cancel some terms. All right, so here we go. Our tangent line, aka our linearization. Okay, linearization. I'll put L for linearization, is our function at a plus f prime of a times x minus a. So for us, that's 5 plus, because that's our function at a, and our f prime of a, 1 over 3 times 25 times x minus 5. X minus 125. Because a is 125. Right there. Here's our a. All right. What's left? Plug in 128. So at 128, the linearization gives what? Well, it's going to be the following. We're going to have 5 plus 1 over 3 times 25 times 128 minus 125. And what do we see? Well, 128 minus 125 is 3. And there's a 3. And we're like, whoa, the 3-ness of it all. So that will cancel. So we end up with 5 plus 1 over 25. And if you like decimals, this is 5. This is the same as 4 over 100, or 0.04. So we're looking for 5.04. So it was C. Yeah, that's not too surprising. Should be a little bit bigger than 5, but not much, since 128 is very close to 125. Nice. All right. Oh my gosh, it's our last multiple choice. It feels like we'd only just begun. But all right, let's do it. Let's do it. Number 6. List the critical points of f of x equals cosine of x plus x over 2 over the interval 0 less than x less than pi. And says a question mark. All right, that's actually a typo. It shouldn't have been a question mark. It should have been a period, right? Because it's not a question. You know, it's not list. It's just like list. It's a command. It's an instruction. Okay, so critical points. Cool. And where are our critical points? Well, look for the derivative of 0 and undefined. And then there's some controversy about endpoints. But notice there's no endpoints. They didn't allow endpoints. Okay, so no controversy about endpoints on this problem. So here we go. The derivative is what? Derivative of cosine, negative sine of x plus x over 2 plus a half. We say, okay, well, not undefined anywhere. These are nice functions. A half, great function. Sine x, also a great function. So if we set it to 0, that says, oh, we're interested, when does sine of x equal a half? All right, well, let's pull out our unit circle for a second and think about what's going on. So we draw ourselves a quick circle. Shoop, shoop. Now, sine. What does sine correspond to in terms of the unit circle? Well, the answer is it corresponds to the y values. The x values are the cosines, the y values are the sines. So if I want to know when does sine equal a half, I'm looking for where does the unit circle hit this line y equals a half. So these are my important places, and in particular, these are my important angles. Now pay attention to the interval you're in. We're in the interval 0 to pi. Depending upon the interval, you may have to adjust slightly. And we say, there are 2 places where we see angles, right? We have this angle here, and we have this angle here. Now, how do we find it? Well, we hopefully know these values. Sometimes we get a table, and sometimes we just say, well, look, it's going to be one of our nice angles, and we just sort of eyeball. Is it 30, 45, or 60? Well, 45 would be more steep, so it's got to be the one less than 45. So that's a 30-degree angle, or pi over 6. what about this other angle? Well, what you can think of is like, oh, see how it's a mirror? So it's like we went halfway around, that's pi, then went back by pi over 6. So it's pi subtract pi over 6, which would mean what? Well, that would be 5 pi over 6. So we are looking for an answer which has pi over 6 and 5 pi over 6. So our answer was B. B. Interesting, interesting. Now, I don't think looking at the multiple choice here, let's see, we had lots of B's, very B's and C's and D's. That is not usual. Don't try to think about it. Some people say, oh, when in doubt, guess C or guess B. That's not a good strategy because who knows? Who knows? Every test is different. Every test is fine. Your test will be different, and so will mine. Now, section 2, the working out problems. We're going to work it out. Great. Good. Maybe it's like our therapy. Like we just need to work stuff out. All right. So we need to show our work. We've already been doing that. So now we're just going to get credit for doing it. Well, okay. Let's get into it. Number 7. Let y be a function of x defined implicitly by this equation. Find dy dx. Now, there's a key word. And one of the things that we want to do as we prepare is we want to learn how to pick up on these keywords. This keyword, implicitly. Yeah, that's a very strong keyword. It tells us what? Implicit differentiation. Now, when we see implicit differentiation, we look at this problem and say, oh, we have a little thought here where it really says, when I see y, think of it as a function of x. And now we don't usually write it down, but we think of it. And so the idea is we're going to take the derivative of both sides with respect to x. So this is not what I would normally write down, but again, just to emphasize what's going on, I'm going to emphasize that every y is really a function of x. So, y of x times sine of x minus y of x quantity squared plus 1 equals 0. All right, here we go. Here we go. So, take the derivative of both sides with respect to x. Now, the derivative of the right-hand side, that's going to be really easy. In this case, derivative of 0 is 0. Sometimes it's not going to be 0. If it's a number, derivative of number is 0. If it's a function, make sure you take the derivative of both sides. But now, derivative of the left-hand side. The first term, x e to the y, that's like x e to the y of x. Product rule. So the derivative of the first, 1, times the second, plus the first, x, times the derivative of e to the y. Well, which is really e to the y of x. So y of x is inside the exponential function. So chain rule. Derivative of an exponential is exponential. So we have e to the y times the derivative of the inside, which is y, and the derivative of y with respect to x, dy dx. Plus, now come here. Well, again, product rule. Derivative of the first, well, derivative of y with respect to x, is derivative of y with respect to x. Leave the second alone. Plus the first, y, times the derivative of the second. Derivative of sine, cosine. Now get to the y squared, which is y of x squared. All right, so function inside a function. It's the square function. So the 2 comes down, y to the power 1, and now times the derivative of the inside. Well, the derivative of the inside, derivative of y with respect to x is dy dx. Derivative of 1 is 0, equals the derivative of 0 is 0. All right. Whew. Now, what do? You start doing your sort of hunting-gathering phase. You say, well, we look for terms with dy dx. There's going to be 3 of those. We mark those. And then we look for the terms without dy dx. And in this case, there's 2 of those. And we're going to mark those. And we say, all right, cool. Now, terms with dy dx are going to go to one side. Terms without are going to go to the other. And doesn't matter which side goes where. So let's put all the dy dx's on the left. And because every term that we're going to have on the left has a dy dx, we can factor that out. So we can say dy dx times, well, x e to the y plus sine of x minus 2y equals, and now these terms have to move across, so we get minus e to the y minus y cosine of x. And finally, we just need to get the dy dx by itself, so we divide by what's attached to it right now. So dy dx is minus e to the y minus y cosine of x. Divide that by x e to the y plus sine of x minus 2y, and that is dy dx. So, great, that's part A. You could do a few things. One thing you could do, at least one thing, multiply top and bottom by a minus sign. It's the same thing. And you don't have to think like, oh man, what's the exact way they're going to write the answer? That's not the goal. Because people grading it know math, and they can tell whether or not your answer is equivalent to a correct answer. So don't worry about like, I got to get it exactly right. Think of it, I got to get it right. And don't put too much stress on yourself. All right, now 3. Find the slope of the tangent line to the graph of the above function at 0, 1. We're not finding the tangent line. We're very specifically, we're told slope of the tangent line. Now, what does slope of the tangent line mean? Like, what's the secret code they've given us? Well, this is secret code for saying the derivative. So the derivative is slope of the tangent line, and then it's the derivative at this point, 0, 1. So how do we do it? Well, we already have the derivative. It's plugging it in. And this notation here means x equals 0, y equals 1. So we have the derivative is, and now go through, everywhere we see a y, we're going to put a 1. Everywhere we see an x, we're going to put a 0. So we have minus e to the 1, which is e. Then minus 1, because y is 1, times cosine of 0. And cosine of 0 is 1. Okay. Divide by, downstairs, x is 0. So we get 0 times e, goes away. X is 0. Sine of 0, 0 goes away. We have minus 2 times 1, which is minus 2. Well, everything has a negative, so we'll just multiply top and bottom by a negative here. E plus 1 over 2, and we're done, because that's what it asked us to find. We're not going to do more than what we were asked. We're here to get the points and to move on. And sometimes when we try to do more, we lose time, we get frustrated, and we're not going to get recognized for it. Get the credit, make sure you do it right, and move on. To number 8. Ooh, a picture. A crane is able to extend its boom, L. So here's L. And look, we know it's the boom because they even wrote that in the picture. The crane can independently increase the angle theta, there's that theta, made by the boom in the horizontal. Great. Now, if h represents the distance between the end of the boom and the horizontal, as shown in the picture, oh, there's h, write an equation relating L, theta, and h. Well, let's not overthink this. Notice this little tiny thing in the corner there. What is that? It's a right angle. We're like, oh, wait a second. This is a right triangle. And what do you have? You have an angle and 2 sides. Which sides? Well, the side opposite the angle and the hypotenuse. So you start thinking, well, gosh, what relates the opposite and the hypotenuse? And then you remember, SOHCAHTOA, where the triangle edges all have names. There's the opposite, the adjacent, and don't forget hypotenuse. SOHCAHTOA. Oh, wait, sorry. Focus, come on, we can do this. We've got plenty of time, but focus. Okay, so what is relating the opposite and hypotenuse? The sine. So we say sine of theta is equal to h over L. And another way we can write that, or we can say or L, or h is equal to L sine theta. There we go. Multiply the L across. There we go. That's it. Part A. 3 points. Ha! Nice. Nice, nice, nice. Now, the real meat. B. If the boom extends at the rate of 3/4 foot per second, and the angle increases at the rate of 1/10 radian per second, how is the height changing at the moment when L equals 15 and h equals 12 feet? Include units with your answer. All right, now let's think about what these pieces mean. So let's go through it piece by piece. Boom extends at a rate of 3/4 foot per second. What is the boom? That's the L. And the word rate means derivative. And so it's like, okay, the derivative of L is 3/4. So we could say, that sinus dL dt is 3/4. Now, quick question. Positive 3/4 or negative 3/4? Now you might say, what? Why are you asking me that question? Well, maybe sometimes they'll say if the boom contracts or versus the word extend. So sometimes they'll have a word which implies either it's getting bigger or getting smaller. So extends is an embiggening term, right? As Jedediah Springfield, embiggen us all, right? All right, so this is a positive. So positive 3/4. Now, you're probably like, Steve, write down your units. Okay, I'll write down my units, but I'm not going to keep doing that. I just do it at the start. Here's the thing about units. They work themselves out. So don't worry about it too much. We'll get there at the end. Okay, so that's that piece of our puzzle. Now let's turn to another piece of our puzzle. The angle increases at the rate of 1/10 radian per second. Okay, so angle, that's our theta. So it's a rate again. So that's the derivative d theta dt is 1/10. And again, it's positive because it explicitly says increases. Pay attention, pay attention. Now the question, how is the height changing? Okay. How is the height changing? Well, changing, that says derivative. So we want dh dt. Okay, so here we go. We're after dh dt, and we have information. We have dl dt is 3/4. We have L is 15. And we also have d theta dt. Do we know theta? I don't think we do. Maybe we don't need to worry about it yet. We'll worry about that when we need to worry about it. All right. Well, let's make couple of notes here. Let's come back up to this triangle. L is 15. H is 12. Could we find this length? Just humor me for a second. Humor me for a second. I think we can. How do we do it? Pythagorean theorem, right? We say, 15 squared is what? Well, that's 225. 12 squared is what? 144. And now, if you take 225 and you subtract 144, you get a number. And you're like, yes, I do, Steve. Yes, I do. You get, the difference of these is 81. And what's the square root of 81? That says this side would be 9. Now, you should actually be kind of suspicious. Here's the thing about triangles. We tend to fall into two categories. Either ones with very convenient angles, 30 45, 90, or 3, 4, 5 triangles. And so this is basically a 3, 4, 5 triangle just blown up. All right, we're going to come back to that in just a second. There's kind of a reason, and bear with me, it'll become clear soon. All right, so off we go. We have L equals 15. And, well, what can we do? Okay, so we're going to take this expression. And we take the derivative of both sides with respect to t. So when we did implicit differentiation, we said, oh, think of y as a function of x. When we're doing related rates, we say, aha, we're going to, again, have a thought, and hopefully we have many thoughts on the exam. We're going to say, oh, h is a function of t. L is a function of t. Theta is a function of t. So we're thinking of everything as depending on t. So take the derivative of both sides with respect to t. We get dh dt is equal to, product rule, the derivative of the first, dl dt, times the second, plus the first, L, times the derivative of the second. Derivative of sine is cosine theta. Chain rule that, and derivative of theta is d theta dt. All right, now comes the magic here. We want to plug in what we know. Well, what were we told? We were told dl dt was 3/4. So we have a 3/4. And what else do we know? We know L equals 15. Okay, that's good. That's 15. And d theta dt, it was 1/10. But what about the sines and the cosines? Because we weren't explicitly told theta, but we were told h. And we say, oh, see, that's why I wanted to fill this triangle in. Because when you have h, you can kind of find theta. But notice we don't actually need theta. We need sine theta and cosine theta. So let's talk sine theta. Sine theta is opposite over hypotenuse. 12 over 15. Okay, so that's sine. Cosine theta is adjacent over hypotenuse. Sorry, hypotenuse. That's where the hypotenuse, I know hypotenuse. Adjacent over hypotenuse. 9 over 15. And now we have all our pieces. And we're like, nice. So we just start cleaning up. And what can we do? Well, we can do things like the 15 here. Get a little bit of canceling going on. Here we can say, look, 12 over 15 is the same as what? They both are multiples of 3, right? Oh, yeah. Yeah, so this is like 3 times 4, and this is 3 times 5, so that's good. And so we can cancel some 3's here. And then we say, oh, well, wait, 4 can divide in, so that cancels. So what do we have? We really have 3 over 5, 3/5. And then plus 9 over 10, 9/10. 3/5, 9/10. And now we're like, okay, well, a common denominator would be 10. So that'd be 6 over 10 plus 9 over 10, making it 15 over 10. And, well, okay, we can now divide both top and bottom by 5. That makes it 3 over 2. 3/2. Now, good. Whew, we worked hard for this answer. And we're not done yet. Because there's a suspicious box here. Because remember to follow instructions. Include units with your answer. We must include the units. All right, well, okay, let's do that. We say, all right, what are units? Well, just think about what we're measuring in. Height is being measured in feet. So this change in height tells us that, hey, since height is feet, this is going to be a feet measurement. And then we have time. What is time? Well, time is being measured in seconds. So it's feet per second. Don't forget that. That's a point. And every point matters. Got to get them all. Got to get them all. All right, well, good workout on that one. Got to keep going. To number 9. A polynomial f of x of the form f of x is negative x to the fourth plus ax cubed plus bx squared plus 16x has a critical point at x equals 1, which is also an inflection point. Find the values of the constants a and b. Okay, so we're told it's a critical point at x equals 1. And not only is it a critical point, that point is also an inflection point. All right. Now, what does that tell us? Well, when will something be a critical point? There's no worries about endpoints, so that totally does not come into our discussion. So we're thinking about derivatives, and the derivative needs to be 0 or undefined. But we've got polynomials. So this is a beautiful derivative. So we're really thinking, aha, where can we say the derivative is 0? Okay, so we're thinking that means that the derivative at 1 has to be 0. That's why we have a critical point there. What about an inflection point? Now, technically, an inflection point is where we change concavity. You're concave up, where you're positive. Concave down, where you're negative. So the only time you can change is where the second derivative is either 0 or undefined. But again, we have a polynomial. Polynomials, we love polynomials. They are our friends, which means there's no undefinedness. So since it's also an inflection point, well, that really means the second derivative at 1 is 0. So we have, lo and behold, 2 pieces of information. And we have 2 things we're solving for. That sounds like a match made in mathematical heaven. So let's go ahead and start digging into this. So we'll start by taking the derivative, and we say, all right, f prime of x is minus 4x cubed plus 3ax squared plus 2bx plus 16. And f double prime of x, okay, now derivative of minus 4x cubed minus 12x squared plus 6ax plus 2b. Okay, and we now are going to evaluate. We say, well, that tells us f prime of 1 is, and the great thing about 1 is you're really looking at coefficients. Minus 4 plus 3a plus 2b plus 16. 16. I already did the computation. 16 subtract 4 equals 12. But don't go too quickly. It's easy to start doing things in your head, and your hand just tries to keep up. You know, be careful. Pace yourself. Pace yourself. All right, second derivative. Well, again, coefficients, negative 12 plus 6a plus 2b. And, that's f double prime. Okay. That's f double prime. One, I should have written that down. And we know these are both equal to 0. So, from here, that tells us that 3a plus 2b and minus 4 plus 16 is 12. Move it across, negative 12. And here we get 6a plus 2b. Move that across, equals a positive 12. And now we look at this, and probably won't have to look too long. We say we have 2 equations, 2 unknowns. And we say, all right, there's a couple ways to solve it. The easiest thing is to say, can you combine them to get down to 1 equation, 1 unknown? That is something we can definitely solve. They both have 2b. So what if we take the first equation and subtract it, and then we have the second equation, right? Minus 3a plus 6a, 3a. Minus 2b plus 2b is 0. Plus 12 makes 24. So that says a should equal 24 divided by 3 is 8. Now that we know A, well, we can say what? We have 3 times A, that's 24, plus 2 times B equals minus 12. We can move the 24 across. 2 times B equals negative 36. So B should be negative 18. All right, B equals minus 18. And remember, what are we looking for? Find the values of A and B. Well, we found them. So we're done. So here, it of course, understand what does it mean to be a critical point? What does it mean to be an inflection point? And 2 equations, 2 unknowns. Bread and butter of calculus. You're going to do that again and again and again and again. So get comfortable doing that. Be comfortable. All right, last problem. Number 10. And we have plenty of time. Almost 20-some minutes. I think we'll finish in time. A cylindrical can with a circular bottom but no lid is to be made from a sheet of metal. What is the largest volume possible, assuming 400 centimeters squared of the metal sheet is used for the sides and bottom? Include units in your answer. And then there's some information here. For a cylinder of height h and radius r, the volume is pi r squared h, and the area around the side plus bottom is 2 pi r h plus pi r squared. That's a great amount of information. Now, let's make sure we understand what the problem is talking about. We have a cylinder, and so we can draw a cylinder. And so here's our cylindrical can, and we're making it out of metal. That seems to be a reasonable thing. And notice that it says, look, there's a bottom part. So this has a bottom, but there's no top. It's sort of an open can, if you will. And then, of course, we have the other thing, which is we have the sides. So we have the sides of the can. All right. So, well, what do we need to know? We have some pieces of information. We know the volume is pi r squared h. And so in terms of this picture, r is this length, h is that length. So volume is pi r squared h because they told it to us. And this is what we're trying to make big. All right, well, good. That tells us that's what we're trying to optimize. And we can tell it's an optimization problem. We should have pointed this out before we got too far along. We were just so excited about these because we saw like an est type word. Large est or big est, most as possible, right? We're trying to make something as large as it possibly can. So it's the volume we're trying to make large. So this is what we're going to be focusing our energy on. And it says, all right, we need to be able to take derivatives and of whatever we're trying to make big and do optimization on it. All right, okay, good. Now, what's our problem? We cannot jump to derivatives yet because there's 2 variables, r and h. We need to get down to 1 variable because that's like the name of our class. Single variable calculus, not 2 variable calculus. So that's where other information comes in. And so these are the constraints, if you will. You say, well, what are our constraints? Well, see how it says there's 400 centimeters squared available for the used on the sides and volumes. And the centimeters squared, that's an area condition. So it's like, oh, so what we get is that the surface area is 400. Well, how do you find the surface area of a cylinder and a circle? Well, the circle, that's like pi r squared. The sides take the circumference of the circle, which is 2 pi r, and then multiply by the height. You can imagine like pulling out a pair of scissors and cutting up along the edge of the cylinder and then laying it flat. One length would be height, the other would be the circumference. Well, okay, and again, that's given to us. So they gave us a lot of good information here. So you have 2 pi RH plus pi r squared. Now, what can we do with this? We can use this to get down to one variable. So we have r's and h's, and looking at this, we say, okay, if we have r's and h's, what would be the easiest thing to solve for? The answer is the h. Why? Because there's one h. If we try to solve for r, we're like, ugh, and metaphorically, maybe literally, the coming from, there's an r and an r squared. That's 2 r's. 2 r's is too many. And so it's easier to solve for h. So we say, okay, we'll say that 2 pi RH is equal to 400, subtract pi r squared, and now divide by 2 pi r. And if we do that, what we'll end up with, well, we can do this in 2 pieces if we want to. Well, maybe let's not do that quite yet. So we have 400 minus pi r squared over 2 pi r is h. Okay. Great. Good. Now, I put a box around it. That's not my answer. This is just like a useful intermediate step. I shouldn't have boxed it. I just love boxes. It's, every day is Boxing Day, even if we don't live in the UK. All right. Now, we're going to take this h and move it into there. So we get the formula: volume is equal to pi r squared times 400 minus pi r squared divided by 2 pi r. Okay. And, well, good news. We get a pi to cancel, which is good, and we get an r to cancel, which is good. And now we can do some distribution. So we have 400 divided by 2 is 200 times r. So we get 200r. Subtract. Well, pi over 2. And then we have r times r squared. And that would give us an r cubed. R cubed. All right. Well, there we go. And, interesting equation here. But all right, once we know r, we're good to go. And so what do? Well, what have we been shooting for? We're doing optimization, which means we need to take a derivative. And what we've been doing is preparing for that derivative by getting down to one variable. And we succeeded. So now that we're down to our one variable, we say, okay, great. Take the derivative with respect to the variable. So we get v prime is 200. And then we're going to subtract pi over 2 times 3r squared. And that's our derivative. Where will the optimum occur? Well, at endpoints or where the derivative is 0. So that's what we're after. Where is the derivative of 0? And the endpoints, by the way, would be a can with like 0 radius, which will have 0 volume, or 0 height, which will have 0 volume. That's not going to maximize it. It's very easy to make badly designed cans. We're not after the easy stuff. We're after well-designed cans. So that's our energy. All right, so rearranging, we get pi over 2 times 3 r squared is going to be equal to 200. Or multiplying by 2 and dividing by 3 pi, r squared equals 400. Divide by 3 pi. And now take the square root. R is going to be, well, okay, square root of 400. That's not bad. 20. Square root of 3 pi. Not the nicest number, but okay, it's the square root of 3 pi. Now, is this our answer? No! Oh, shoot, I shouldn't have boxed it. But what we're going to do with it, this is where the max occurs. Oh, well, that's useful. We can now plug it into our formula for volume, because we have our formula for volume in terms of R. And so once we plug this into here, we have our answer. Ah, nice, nice. Okay, so we're rounding the corner. The end is near. So what do we have? Well, we'll get that our volume will be equal to 200 times 20 over square root of 3 pi minus pi over 2 times 20 over square root of 3 pi cubed. All right. And we probably should simplify this. All right, so let's do that. So this would be 4,000 over the square root of 3 pi. Here we have minus pi over 2. And now here, 20 cubed would be what? Well, that would be 2,400, 8,000. Wow, 8,000, that's a big number. Divide that. Now downstairs, square root of 3 pi cubed will actually be 3 pi times square root of 3 pi. And, well, okay, good news. The pi's cancel. 2 goes into 8,000, leaving us with 4,000. And so that's 4,000 thirds. And now, well, okay, so keep going, keep going. You can do it. You can do it. We want to get a common denominator. This has square root of 3 pi. This has 3 square root of 3 pi. So multiply the first one by 3. So 12,000 over 3 square root 3 pi. And subtract 8,000 over 3 times square root 3 pi. Gives us what? It gives us 4,000 over 3 square root 3 pi. Okay. Oh my gosh. Oh. I was looking back and I realized I did something incredibly stupid. Notice here it says 8,000, but I crossed it out. It should be 4,000. So this should be a 4,000, and 12,000 minus 4,000 should be 8,000. Oh my gosh. Pay attention. Pay attention. It's easy to make small mistakes. Now the good news is when you're doing long answer problems, small mistakes, a point, maybe 2, especially towards the end. Small mistakes at the beginning can be dangerous because they can often snowball out of control. Okay, so the answer is 8,000 over 3 square root 3 pi. Now, where did we get the centimeters cubed, right? Well, remember, we've got to include units in our answer. And they gave us a big clue. They said, oh, area is centimeters squared. Everything's being measured in centimeters. So centimeters cubed, that gets us our volume. Whew! Wow. What a problem, right? What a problem. And, well, it's a little bit involved. The ideas, though, aren't bad. Do the process. Do the process. You can do these problems. You can do this problem. Now, this, of course, is not going to be your problem, but you can do these types of problems. Everything we talked about, you're capable of doing. Keep up what you're doing. Keep up your practice. Keep working hard. I believe in you. I believe in your potential and your ability to do great things. And you're going to be okay. Do the work. You're going to make it. You're going to make it. And then we'll see each other again on the next exam, right? All right. Good luck. Hope you do well. Bye.